I literally went through in 4 days, I spent 2
You're in the mall.
because I'm such a straight butterfly. I love it's a month of children. I'm telling you, I live in like I got my own drink, I don't ever drink again. It's so bad. Like my boyfriend, ex-boyfriend. Your guy. My dude. Yeah, I cannot. He tells me.
Okay, so I gotta start the class. Here's kind of what the data and the test looked like. Where I designed the test to kind of average around 70, and 70 being the.
Design it so people would get average.
That's what average means. So, but I mean, the idea is that the average being, at least maybe not the test, but the class in general, the way the curve is, that the average of the class is 70. That's a B minus C plus, and a standard deviation about 15. That means that so 68% are within 1 standard deviation of the mean. And what we had in the test was there were two distributions. There was a real spike set around 25, and then there was a really broad distribution over here. So really, if you got rid of the spike, the class fits into the general distribution, with the exception of it's a little more broad than normal. So, but people have been asking me about the test. So what I'm doing right now, some people have missed the test, and I give them a week to make up, and then the week's gonna be over on Wednesday, and then that means a week from today I'm gonna pass back the tests, and I'm gonna post an answer key with the solutions, so that way you can see what you did wrong. So then I'm going to put an optional retake in the testing center at the Learning Center. And that way you can go and take the test, and I'll just take the higher score. But then again, you can also see what you've done incorrectly and work off those corrections. Does that work for you guys? And about the problem session, didn't get too many responses, but it seemed like the best time for everyone was after this class on Wednesday.
Did you
There was
email?
the same announcement.
Yeah.
Oh.
Yeah, but it's I emailed to UH. It's supposed to get all the UH emails.
It's in the same. Okay, never mind. Continue.
It's at the bottom.
Continue. I'll look at this independently.
Okay. Does anybody need anything else? Is there anything else that you need that's not being provided, or give me some feedback here? No, you're all okay. Because the score was a little low, but that's, I mean, part of it is this big spike at 25. And the thing is, we had 20 questions and one was a freebie. That means that I had like 3 students that had 25, I had one that had 20. And I mean, if you took away those grades, actually the score was pretty good. The average was pretty high. But these students, a lot of it was just by chance, actually, because there were 5 questions, 5 options, and 20% would be by chance, and 25, and then plus 1 for the freebie. So really your probability would put you at 20 or 25 points. So that's. And so the retake, I wanted to make it due. I looked up the date. It's November 4th. That's a Monday. It's the last day to drop. So I want to make the retake due on November 1st. And I'm sorry I have to pick that date because that's the day after Halloween.
Oh no! Oh. Oh wait, no, I'm not doing it anymore. Never mind. It's totally fine.
You can take it on the 30th. But
Anyway, I'm not celebrating mommy.
but I mean, that way you can look at this and think, okay, do I need to continue? I don't like to lose any students to dropping, but I understand people have things going on, and I mean this class it's called stratification. No, it's not scaffolding. That's what the term is, scaffolding, because I mean everything you learn you have to use for the next step, and then the next step, it builds up. So if you're not getting the beginning stuff, it's going to be a rough semester for you. At the same time, if you can put it together at the end. I mean, if you want to keep on going, I'll always encourage students. But and I do get students that are C's or D's, and then they get A's at the end. So they can just, a lot of times they can ace their final. I've seen that happen here for around 5 or 6 students, and about 10% of my students score better on the final than they do on the class on average. So, I mean, putting together at the end is a possibility. So.
Yeah, I think the first test is, I mean, from my experience, is always kind of like the framework, and then you just get better and better and better after that.
Good. I hope that's
You
the case.
You feel the teacher's tests.
All right. But does anybody have any questions before we move on? Unfortunately, we do have to keep on going though, because we have 2/3 of the course material to go through, and it's already the middle of October. No questions? No questions? Okay. So this is where we left off. So we derived this formula back 2 weeks ago. Density is pressure times molecular weight over RT. So what is the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeters of mercury? So you're wondering, and I mentioned this before about these pressures, if you're wondering where they come from, there's an apparatus, they call it a U-tube apparatus. So imagine you have a vessel, and this can be connected to what is referred to as a U-tube apparatus. And this is what a U-tube apparatus looks like. You'll never guess why they call it a U-tube apparatus. And of course out here is 1 atmosphere. And inside of it you have mercury. And the difference in the level of the mercury. So you'll have mercury there, and this would be a high pressure. Since this is pushing the mercury up this way, that means that the pressure inside the cylinder, and then you could take the level on the U-tube, and you could just take a meter stick and then put it right here and then look at the height. And then that means the pressure inside this vessel would be the atmospheric pressure plus this many millimeters of mercury, and then in the lab there was a barometer as well. So if you know the outside pressure, you know the difference in pressure, you can figure out the pressure inside the chamber. So that's also the difference between what's called gauge pressure and absolute pressure. So like when you check the pressure on your tires, so you say your tire pressure is 32 psi, it's not really 32 psi, it's 32 psi plus the atmospheric pressure. So the atmospheric pressure is usually around 15 psi. So, but anyways, this is, if you're wondering why we keep on having millimeters of mercury, that's how they used to do it. And 760 millimeters of mercury, about this much, is the same, the weight of this is the same as the atmosphere weight from sea level up to 60 miles up, same as 10 meters or 33 feet of water, and 14.7 psi. So these are all 1 atmospheres. And you'll be given those numbers. Am I blocking you, Peter?
No, I'm just.
Are you just swaying your backwards? Trying to crack it? Okay. Well, let me go ahead and do this calculation. Calculate the density of nitrogen gas at 125 degrees Celsius, and
Is
so
that fancy M, is that molarity?
molecular weight.
What's the R?
R is 0.08206 liter atmospheres over mole Kelvin.
But what does it stand for?
Gas
Is it
law
constant?
constant. It's Avogadro's number times what's called the Boltzmann constant. But it's R is known as the gas law constant.
So R is a constant.
Yes. R is a constant, it does not change.
Gas law constant times
Temperature.
And then you said molecular weight, like just the weight of the element.
Yes. well, in this case, molecule. Because nitrogen gas, this is 28 grams per mole. So nitrogen is 14. So anyways, let me do the density calculation here. So pressure is at 755. 755 millimeters of mercury times atmosphere over 760 millimeters of mercury times 28 grams per mole all over 0.08206 liter atmosphere over mole Kelvin times temperature 398 Kelvin. So 125 degrees Celsius is 398 Kelvin. Again, you get any conversion factors. I think I'm gonna cheat and look it up in the book, unless you really want me to put it in the calculator. I can. I'm feeling my brain's a little slow right now. Boyle's law. It's not Boyle's law. Which example is this? 6.7. All right, here we go. 0.08, 0.852. What the heck?
It's my energy.
0.852, and the units are grams per liter. Okay. Is that bugging you? Do you want me to?
I like it when it's on. I don't like it when it's off.
Okay, I can try and turn it off. Well, this one was blinking over here too. Okay, so recap for this one. This is just a plug and chug calculation. So you put in you have one equation, you put in the numbers. In this case, pressure is 755 millimeters of mercury. They convert to atmospheres because our R is in units of atmospheres. And then molecular weight, 28 grams per mole. Over RT, R is there, T, 398 Kelvin. And we get 0.852 grams per liter. So what? Well, density of water, liquid water, is 1 kilogram per liter. So if you have a liter of water, this is about a liter of water, it weighs about a kilogram. And now we have nitrogen, that's 0.852, so less than a gram per liter. So what does that tell you? That tells you that gas, so air, is about 1/1000th the mass or the density of liquid water. So right, so if you try and move your arms in air, I can feel the wind. It's pretty easy. What about doing that underwater? It's a lot harder, right? Moving your arms underwater is a lot harder. Why is it a lot harder? Because you're pushing 1,000 times as much matter out of the way. And if you've ever seen, has anyone ever seen a hydroelectric plant before? No. They're tiny. If you ever see a hydro plant, they're tiny. Compare that to a windmill. Do you think windmills are big or tiny? They're big. Why are they big?
Produce more.
Yep, air. There's not a lot of energy in air. It's just because air is so diffuse. Maybe if we were on Venus or Jupiter or something that has a really thick atmosphere, then our windmills could be tiny. But here on Earth, the air is much thinner. So it tells you about gases. Gases are pretty thin, generally speaking, especially at ambient pressures. Okay, so anybody have any questions about that? Okay, so next thing we do is talk about Dalton's law of partial pressures. So, and we haven't talked too much about ideal gases. We'll talk about that on Wednesday. But ideal gases, the idea of an ideal gas is it doesn't interact with other gases, other particles. And because of that, since there's no interactions, that means that the pressure of something is just additive. So if there's no attraction or repulsion for gases, and it's usually attraction would bring the pressure down. It's like if I take an atmosphere of oxygen, I mix it with an atmosphere of carbon dioxide, and then an atmosphere of nitrogen, it would just be 1 atmosphere plus 1 atmosphere plus 1 atmosphere. And then the total pressure would just be the sum of the pressure of each of the gases. And that may seem like common sense, but with that though, it's the idea the gases don't interact at all. If the gases interact, if they attract to each other, then the pressures would be less. They would you mix them together, and then the pressure would be less than the sum of all of them together. But for ideal gases, it's just adding them all together. And that's Dalton's law of partial pressures. And then we have the mole fraction. So mole fraction is just the number of moles of whatever over the total number of moles. So if you have 100 moles total, and then you have 70 moles of nitrogen, so 70 moles over 100 moles, that's a mole fraction of 0.7. And I don't know why this textbook does it this way, but everywhere else uses Y instead of X for mole fraction in the vapor phase. So in the liquid phase, it's usually X. For the vapor phase, it's usually Y. You see that in engineering textbooks. Also, has anybody heard of the Code of Federal Regulations before, the CFRs?
No.
I've heard of that. Okay, so the federal government has a bunch of laws called the Code of Federal Regulations, or the CFRs, and they're all sorts of things. So labeling laws. I don't know what the CFR is for labeling laws, but there are labeling laws that say how big to make the font, what font to use, what colors you can use the font, right? And in what order you can list your ingredients in. There's laws about that. And for instance, I know that the chemistry lab law is 23 CFR 1910. So that means that it's a 23rd volume of the federal laws, law number 1910. So that means that there are at least 2,000 laws in the 23rd CFR. I don't know how many CFRs there are. I only know the ones that really pertain to me. But there's a subset of emission laws called RCRA. That's part of the Code of Federal Regulations. And so they have equations in them. So you're allowed to pollute so much, and you have to show that you're in compliance, and they have equations to show you how to calculate that. And in those equations, they have Y. I know this because one of my sisters did this, and she was having trouble with one of them, so she called me up to ask me for help. So it made me feel really special and important. But I explained to her what the equation meant. And I remember it was dealing with the amount of pollution and that was allowed from rail cars. And I explained to her what the terms meant. But, okay, because she had to give a presentation. Anyways, well, okay, so, but the idea here of the mole fraction, the pressure of whatever is just a mole fraction times the total pressure. So let's look at some of these. So here is a mixture. A 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 Kelvin. Partial pressure of helium is 341 millimeters of mercury. Partial pressure of neon is 112 millimeters of mercury. What mass of argon is present in the mixture? So here is my breakdown of this. We have a vessel. The vessel, which I draw as a poorly drawn cube, has a volume of 1 liter, temperature 298 Kelvin. We have a mixture of helium, neon, and argon. Total pressure is 662. Pressure of helium is 341. Neon is 112. And we need to know the mass in grams of argon. We don't know the pressure of argon, but we know that the pressure of argon is going to be the total pressure minus
What does
the...
this say? PK,
Which one?
the third one down on the right.
Helium. He.
Oh,
Is that better?
yes. PhD. Oh, pressure of helium.
Minus the pressure of neon. So because pressure of helium plus the pressure of neon plus the pressure of argon equals the total pressure. So the pressure of argon is just total pressure minus the other gases. So this is going to be total pressure is 662 minus 341 minus 112. I know my foster cat's been keeping me up. Minus 341 minus 112. This is 209. So the pressure of argon is 209 millimeters of mercury. So now that we know the pressure, how do we find the mass? Well, we can find the mass from the number of moles of argon times the molecular weight, 39.95 grams argon per mole argon. If we figure out what the moles of argon are, we can multiply it by the atomic mass from the periodic table. And how do we figure the number of moles? Well, PV equals nRT, or you can solve for n. N is equal to PV over RT. So you can plug that in, 209 millimeters of mercury times atmosphere for 760 millimeters of mercury. Volume is 1 liter all over R, 0.08206. Liter atmosphere over mole Kelvin. Temperature is 298 Kelvin. Is it 298 Kelvin, right? Yeah. So you put that in your calculator that I had on the table. 209 divided by 760 divided by 0.08206 divided by 298. And we get equals 0.0112 moles argon, then 0.0112 times 39.95 grams argon per mole argon times 39.95. And we get 0.449 grams of argon. Okay, so recap for this one. We have a reaction vessel that's size is 1 liter. Their temperature is 25 degrees Celsius, 298 Kelvin. Total pressure is 662 millimeters of mercury. The pressure of helium is 341. Pressure of neon is 112. We want to know what the mass of argon is inside this vessel. So the way we do this is we're going to figure out the number of moles of argon. To figure out the number of moles, we need to know the pressure. So we take the total pressure minus the other pressures to figure out the partial pressure of argon. Now that we know the partial pressure of argon, we can use the ideal gas law to solve for moles argon. Once we get the moles argon, we multiply by the atomic mass of argon, and then we get the mass of argon in grams. And that's what we want. Questions with this?
So you went from pressure to moles to partial pressure to mole to mass.
From pressure to partial pressure to moles to mass.
Where did that 760?
That's a conversion factor. An atmosphere, because the unit R here is in atmospheres. So you either have to put R in millimeters of mercury, or you have to convert millimeters of mercury to atmosphere. The way I do it, and the way the book does it, is that you keep the value of R, and then you convert the units in your calculation to the proper one. Other questions? So Air is actually about 0.9% argon. So if you look at air, like air, and this is dry air, there's usually a little bit of water in all air here on Earth. Maybe not during the wintertime in Antarctica, then that might be completely dry air. But really everywhere else, there's a little bit of water and air. But this is what's in dry air, and it's more or less consistent across the world. And we're about 0.9% argon, and this is important because they found out that when you have a reaction vessel, I mean, what most people try to do is they try to recycle things. So if you have an input into a reaction vessel, and then you have an output, the next example we're going to go over deals with methanol. So you can have the chemical reaction take place in this vessel, and then you shoot the air or the gas, and then you can go and you can compress it down. When you compress something down, you can draw off a liquid product, and then you can shoot. You're like, okay, well, you know what? Why don't I just do it this way? I'm going to have my reactants go in. I'm going to have a reaction vessel, and then I take the products, I go out, and then I'll compress it down. So if I want a product, and this works for many things, methanol, also what else? Ammonia. Ammonia is a big one. We make a lot of ammonia. And then that turns into a liquid, you draw off the product, and then now you have a mixture that has the reactants in it. So what do you do with the reactants? Let's just throw them back in the reactor and let it keep on going. And I mean, it makes sense. It's recycling things. The problem is if you do this, air is usually a reactant. Air is usually a reactant, and since argon doesn't react, it gets stuck in the reaction vessel. And then as time goes on, you actually just end up filling your reaction vessel with argon. So the way that they get around this is they have a purge line. So you actually have to purge your system. You can recycle it a little bit, but you can't always recycle it infinitely. So, but that's what they found out by trial and error. Otherwise, like, oh, this works great until a while, and then it stops working. And that was also before they figured out, like, oh, there's argon in air, and that's not reactive. So, also with that, the mixture of air. So why do we care? So scuba divers, and for scuba divers involved, this is for all humans. So air is about 0.205% oxygen, and we're very well equipped for that. And if you go below that, you can, most humans are kind of uncomfortable, especially when you get to 10,000 feet. I'm the lucky duck that gets uncomfortable at about 8,000 feet. So I'm prone to altitude sickness. I'm uncomfortable at 10,000. I'm really uncomfortable at 14,000. So, and then that's getting close to hypoxia. So most people, like I said, most people get uncomfortable about 10,000 feet. And that's lack of oxygen. So, and also, oxygen is a good old moderation argument. So having too little is bad. Also, having too much is bad. You can actually get oxygen toxicity. And we can breathe pure oxygen. I've never breathed pure oxygen before. I've never tried that. Well, at least, I guess I have for the little gas cylinders. I've never done the oxygen tent or whatever it is. And this isn't a big deal for us at sea level, though, even breathing pure oxygen. But if you're scuba diving, so the partial pressure of oxygen in air right now is about 20%. But then if you go down 30 meters, so 10 meters of water is an atmosphere. So you have 1 atmosphere from the atmosphere of the Earth, and then 3 atmospheres from the depth of the ocean. Your partial pressure of oxygen in the lungs increases to 4 times that of ambient pressure. And this is still fine. So you can go 100 feet, 30 meters underwater, and be fine because you're still in the safe range. But what happens if you go down further? So you can get to these places here where you're at maximum exertion. And the people that have experienced this, they tell me that you feel anxious, your heart is racing really fast, and you don't breathe very much at all. So meaning like you'll breathe once like every 2 minutes. So of course if you're in this end, you're breathing a lot. I gotta go up the stairs like, gosh, I can't catch my breath. Here you're like up the stairs. I'm like, that's weird, right? So like I don't need to breathe very much because there's so much oxygen in the air. So how do they get around this? For really far depths, they use what's called heliox, a mixture of helium and oxygen, and a lower concentration of oxygen as well. And this is a problem for a few things. Right now, helium is an endangered element. Helium is way under market value, and it's considered an endangered element. And why is it undervalued? Why is it so cheap right now? Well, we here in the United States, we stockpiled a bunch of helium right around World War I because we use it in warfare. Specifically, we used it for getting rid of submarines. So when I guess they're called U-boats at the time. I guess they're still called U-boats. The German U-boats, when they would attack flotillas, if there was a blimp overhead, the blimp would see the submarine, the U-boat. They could see the U-boat, and then they would follow the U-boat until the U-boat had to surface, and then they would bomb it and sink it. So blimps followed alongside flotillas and around World War I. And so in the United States, what we did is we stockpiled a bunch of helium. Then we sat on it for a while. Then Congress said, like, hey, why do you have all this helium? We don't need this helium. Get rid of it. So they've been getting rid of it at like a really, really fraction of the price that it's worth. And we're almost out. So that's a problem. It's a problem for things like scuba diving and other things like superconducting magnets and various things that need helium. Okay, so what about, and the other thing with helium, they use helium in scuba diving for down far because it prevents a condition called the bends. So the bends is when you have nitrogen, so the same idea. You have nitrogen, and if you go down far enough, I haven't scuba dived before, but if you go down far enough, you can get a condition called nitrogen narcosis. And that's where nitrogen acts like a drug, like a narcotic, and you get high. It sounds like fun, but say you're an underwater welder and you're welding underwater, suddenly you start giggling incoherently and then you start doing stupid things. So that's where narcosis can be dangerous. But also where it's dangerous is if you ascend too quickly, you can get nitrogen bubbles in your bloodstream and it creates a condition called the bends, where you bend over. And that condition actually was discovered in the building of the Brooklyn Bridge in New York City. So they had workers that went underground, and so, I mean, can you imagine that work? That must have been hell. I mean, going underneath the Hudson River in the dark, to work underneath there, and when your shift is done, what do you want to do? You're like, I want to get out of there as fast as you can. So the people are like, all right, I'm done. Like, all right, let's go jump in the elevator and jump up, and like, oh, what a beautiful day. Oh, and they're like, I can't move. Like, what's wrong with Mike over there? Like, oh, he's got the bends. It's called the bends because the bubbles boil, and then people hunch over because it hurts to move around your joints. You would, your back and your knees and elbows, you just kind of bend over like that. So that's why it's called the bends. So how do you cure it? You ascend slowly and adapt. So is there another way?
I mean, that's not a cure. Like, that's how you prevent it.
Yeah.
Like, you have to be repressurized.
Yeah.
To decompression chamber.
Yeah. I guess I stand corrected. You repressurize to dissolve the nitrogen back in your bloodstream. So, okay, so hopefully you can get this. Is supposed to be an easy question. So air is 78% nitrogen. What is the partial pressure of nitrogen at 1 atmosphere? How many think it's A, 0.78? How many think it's B, 0.22? How many think C? You guys are, is today a rough day? A lot of people look tired.
It's Monday.
It's Monday.
Monday is a good day.
My
I know
brain's
my classes don't start until noon.
Oh my god, my classes start at 9. I have to take the 7:30 bus.
my brain is a
Mondays
little.
are so long, it's the longest day ever.
I must admit, my brain is a little slow today too.
I
And
must admit, I didn't read and I have no idea what you're talking about, so that's
I'm on
why.
that page.
well, good. Hopefully, the melodious sound of my voice and explanations is so clear.
It'll make sense.
I
next
stopped, I
time.
went to go read, I was like, I need to figure out what he's talking about.
What are you confused about?
Oh no, I'm not even paying attention now. I know about the nitrogen, I mean, I don't know anything about the nitrogen bubbles, but I watched the movie 47 Meters Down.
Never seen that.
You should watch it, it's all about, it's actually really, really scary. It's a good scary movie.
Okay. Does anybody have any other questions about something before we move on? Okay. The next thing I'm going to talk about is vapor pressure. So, vapor pressure. So, let's say we have a reaction here, zinc and hydrochloric acid that produces hydrogen. It's going to come over here. It's going to bubble into this water vessel, and then the bubbles form, and over this water here you have hydrogen, and actually you have a little bit of water in there. And where does this water come from? This water comes from a phenomenon called vapor pressure. The way that the vapor pressure is modeled as, the idea is that the liquid puts a pressure on its surface. And then that pressure, when this internal pressure of the liquid equals the external pressure of the vapor, as the internal pressure here of the vapor pressure equals the ambient pressure, liquid boils. But also that vapor pressure is equal to the fraction of gas above that. So for instance, the vapor pressure of water at 100 degrees Celsius is 1 atmosphere, 760 millimeters of mercury. So that means that when the ambient pressure is 100 degrees Celsius, if the ambient pressure is 1 atmosphere and the temperature of the water is 100 degrees Celsius, water will boil. So if you increase the pressure past 1 atmosphere, water will boil at a higher temperature. If you decrease the pressure, water will boil at a lower temperature. And that's the idea behind a pressure cooker. So if you ever use a pressure cooker, you increase the pressure of water, and then it cooks things faster, right? And if you've ever used a pressure cooker as well, what do? You have to like let the steam out before you can eat from the pressure cooker, because the steam's under pressure. And another thing with that, though, so why do you use pressure cooker and use water? What's so special about that? Remember we talked about the liquid phase versus the vapor phase, that at least at this temperature and pressure for air, there's 1,000 times as much matter in water as there is in air. So cooking turkeys. How long does it take to cook a turkey in the oven?
All day.
All day. I think it's less than that, like 4 hours, depending on how big your turkey is. How long does it take to cook as in a deep fat fryer? Yeah. So why is there this huge discrepancy? Why does it take 8 times as long in the oven than it does in a deep fat fryer? And the deep fat fryer, you don't even heat it up that hot, right? It's like 250, 300.
Well, it's like one's liquid and one's gas, and completely consumed by an extremely hot liquid that has density.
Yep.
In the oven, it's just hot gas molecules.
Yep. And more collisions means more heat transfer. So that's why. So more density means more collisions, means more heat transfer. So heat transfer is much more effective in the hot liquid than it is in a hot gas. So that's the idea behind a pressure cooker. Anyways, let me go back to this, the vapor pressure. The vapor pressure, the idea that a liquid puts pressure on the surface, that's not real. What's real is this. So if you look at number versus kinetic energy, so number versus kinetic energy. So this would be a low temperature. Here, I'll do orange. Actually, no. I'll do purple. Why not? Here's a medium temperature, and here is a high temperature. So let's say that this is the amount of energy that it takes to boil. Okay. All right, let's talk about the states of matter. So let's pretend that these are water molecules. Here's a solid. Okay, water molecules like this. Solid has a set shape, set volume. Temperature is average kinetic energy. So average translational kinetic energy. So it starts to heat up, heat up, heat up. Suddenly the solid melts because there's enough energy to break the bond between them. The liquid heats up, heats up, heats up, and then it flies apart. This is the vaporization. So the energy, the kinetic energy is enough that it breaks the bonds between the molecules. So your solid, your melting point, your boiling point is a direct measurement of how strongly bound the molecules are. And if you have a low temperature, the temperature is average kinetic energy. It's a distribution. You have a tiny bit that has a lot of energy. And that means for a low temperature, you're going to have a little bit of the liquid that has enough energy to escape. And for a medium temperature, you're going to have a higher fraction. For a high temperature, you're going to have a great fraction. So as temperature goes up, there's the higher fraction of the liquid that will be able to escape. That's really the source of the vapor pressure, not this magic pressure that's on the surface of the liquid. It has to do with numbers and probability and energy. But you can think of it like the model says, that the vapor pressure is a pressure that the liquid exerts. But that model makes more sense though, because when the ambient pressure equals the vapor pressure, liquids boil. And that's also how we get instant coffee. So how you get instant coffee is you make coffee, and then you draw a vacuum, and then the water boils away, and then you're left with coffee powder. So that's better. You can also make instant coffee by boiling it, but I don't drink coffee, but apparently...
It's disgusting.
Yeah.
Oh, instant. I thought that would be drank.
Oh,
Like you would
instant
like
coffee.
burn it.
Yeah.
Yeah, it's,
That sounds terrible.
no, yeah, it is. I switched to green tea while I was in China. That's all that they drink. Coffee beans aren't imported. Anyways.
I like my coffee strong enough in the morning to put chest hairs on.
All right. But
Go get some water.
I didn't think I'd excite you guys by talking about coffee, but okay. So here's a chart showing vapor pressure versus water, or vapor pressure versus temperature for water. This is something you don't have to memorize. These data will always be given to you. So you don't have to memorize any of these things. And this one is circled because it deals with our next problem, collecting gases over water. So in order to determine the rate of photosynthesis, oxygen gas emitted over an aquatic plant collected over water temperature of 293 Kelvin or 20 degrees Celsius and a total pressure of 755.2 millimeters of mercury. Over a specific period of time, 1.02 liters of gas is collected. What mass of oxygen is formed? Okay, so here is my beautiful artistic picture of this. And so let me write down some of these. And we have 1.02 liters and 293 Kelvin equals 20 degrees Celsius. Okay. So same idea. We have algae, which looks like green spaghetti with dots on it. That's how I draw algae. So we have some algae in here, and we are seeing how much oxygen is being produced. And we have this algae in water, but as the oxygen is forming, it's not just oxygen in here, we also have water vapor. And so what we're looking for is the mass of oxygen. So why do we care? Well, we're looking to go to Mars. And if we're going to go to Mars, we got to find a way, and it's going to take about a year or so, depending on when we leave with respect to our orbits. It's going to take about a year to get to Mars. And for people, we need to find a way to get people to breathe and we also need to find a way for people to eat. And how are we going to do that in deep space away from Earth? We're probably going to do that with algae. So we're probably going to have algae, an algae bioreactor, and we've already done this. We can take algae, we can tweak it to make fats, proteins, and carbohydrates, so different strains, and also they all produce oxygen. So that way we can manufacture our macronutrients on the way to Mars, and then when we get to Mars, we can manufacture our macronutrients there on the surface. So, okay, and if you're trying to figure out how much oxygen each astronaut needs, this is an important question. Okay, so we have this thing. We need to figure out the mass of oxygen in this reaction vessel. So the same idea, the total pressure. So the total pressure is 755.2. This equals the pressure of the oxygen plus the pressure of the water. So that means that the pressure of the oxygen, this is the total pressure minus the pressure of the water, which is 755.2 minus the vapor pressure. And we go back to the chart, and here at 20 degrees Celsius, it's 17.55. So 17.55, and what is that? Oh, wrong problem. 737. 37.65. Is that right? Yep. Okay. Millimeters of mercury. Okay, so we have the oxygen pressure, and this becomes the same as the last problem. So we need the mass of oxygen, and we can get that from the moles of oxygen, and we can get the moles of oxygen from the ideal gas law. So same as before, PV equals nRT. N is PV over RT, where you have 737.65 millimeters of mercury times atmosphere over 760 millimeters mercury. Temperature, oh no wait, volume, it's 1.04, is that 02? Liters over R, 0.08206. Liter atmosphere over mole Kelvin times 293 Kelvin. Okay. And you put that in and you get 4.12 times 10 to the minus 2 moles oxygen. Then you have 4.12 times 10 to the minus 2 moles oxygen times 32 grams oxygen per mole oxygen. And in doing so, you get 1.32 grams oxygen. Okay. Recap for this one. You're doing research to see how much oxygen and food we can get to our astronauts using this particular strain of algae. You're trying to find the best strain of algae to go to Mars and then live on Mars. and you're trying to calculate how many people, how much algae you need and how many people it'll support. So you're doing these experiments, and you look at the volume of gas here at the temperature. You want to know, hey, what's the mass of oxygen that I'm generating in this? So, but you can't forget to drop out the partial pressure of water. So it's the same one as last time. You have the total pressure is equal to the pressure of the oxygen plus the water. So the pressure of the oxygen is actually the total pressure minus the vapor pressure. Luckily, you have a chart. You can look at those data. And then now, how do you figure out the mass of oxygen with that pressure? You apply the ideal gas law to get the number of moles of oxygen, and then using the molecular weight of oxygen, 16 times 2 for oxygen, or 32, you get 1.32 grams of oxygen for this example problem. So, questions on this? And this illustrates another point of the reason why people hate chemistry so much. People hate chemistry, among other things, is because you can't forget anything, right?
Yeah.
You cannot, all the stuff you learn in the beginning, you're going to be doing this for the rest of the semester. So you cannot go and do a brain dump, like, oh, thank God I'm done with chapter 5. It's all gone. Okay, let's go into chapter 6. No. The stuff from each and every chapter is going to come back to haunt you for the rest of the semester. So no, but I know a lot of people do not like this class. I don't take it personally. It's one of the hated classes in college. So, but anybody have any questions with this? All right. Next example. And now what we're going to do is we're taking the ideal gas law, we're combining it with the chapter 5 stuff you learned. So, and chapter 4 and chapter 5. So, actually no, it's not chapter 5, this would be chapter 4. So, methanol can be synthesized by using this reaction. What volume of hydrogen at a temperature of 355 Kelvin and a pressure of 738 milliliters of mercury is needed to synthesize 35.7 grams of methanol? Okay, so we have this equation here. So we need 35.7 grams of methanol. Me is methanol. So 35.7. And we need volume, we want to know volume of hydrogen. And this is at 355 Kelvin and a pressure of 738 millimeters of mercury. So we have this chemical reaction, and we're given a product. So how are we going to figure out, so this is the product. So it's on the right, of course. This is the product. And we're saying we're making this much methanol. How much reactant do we have? Why would you care? Why would you know this? Let's say that you're a plant manager or an engineer or a purchaser in the plant, and then you got to figure out how much reactants you need to make your products. Of course, if this was a plant, you wouldn't be making 35 grams. You'd be making 35,000 tons of it. But we'll stick to the small numbers now. So how do you figure this out? So you have to combine dimensional analysis. So dimensional analysis, and from dimensional analysis, you can get the number of moles of hydrogen. And if you get the number of moles of hydrogen, you can get the volume. So you start off with what you know, 35.7 grams methanol. Let's write out the whole structure. Methanol, so 12 plus 4 plus 16, this is 32 grams CH3OH per mole CH3OH, and then we have 2 moles hydrogen to every mole methanol. So that's going to be about 2 moles. Oh wait, no, I got it backwards. No, I got it, shoot. Oh. I got this backwards.
I'm gonna have to just throw away the problem.
Throw away the problem. Because I wrote the fraction wrong?
Mm-hmm.
Okay. Jeez, it's a tough crowd.
Isn't the last one backwards too then?
No, that's right, because moles
Oh,
cancel.
yeah.
And putting in our calculator or looking at the book, then you get 2.23. This is 2.23 moles hydrogen. So now we're looking for volume. PV equals nRT, or N equals PV. Oh, we need volume, shoot. I'm so used to solving for N. Volume is nRT over P, which is 2.23 times R, 0.08206 liter atmosphere over mole Kelvin. I should put temperature is 255 Kelvin. Pressure 738 millimeters of mercury times atmosphere over 760 millimeters of mercury. Okay. So then you put that in your calculator and you get 66.9 liters. And that's your answer. Okay, so recap for this one. We have this chemical reaction. So forming methanol. And we know that we want to have 35.7 grams of methanol product, and we have an input stream of hydrogen gas at 355 Kelvin and 738 millimeters of mercury. We want to know how much hydrogen we're going to use for this. So how do we figure that out? We take the product, and then by dimensional analysis, we get the moles of reactants, and plug that in to solve the ideal gas law equation for the volume. We plug in the number of moles, and then doing that, we find out we need 66.9 liters of hydrogen gas at that temperature and pressure. So, questions with this one? So again, now your job's not only you can't forget everything, you have to take all the concepts, you have to blend them together in your head. So that's the other thing that people hate about chemistry, right? You gotta integrate all this knowledge. And a real brief history lesson with this though, this mixture of carbon monoxide and hydrogen, this used to be called town gas because they used to send this to homes to heat homes. We don't really need heat here in Hawaii, but everywhere else in the country, basically you need to heat your home in the wintertime. And they used to use, well, they said town gas to heat the home. What's the problem with it, do you think? Well, that's true for methane too, but carbon monoxide is poisonous. If this is an odorless poisonous gas, so a lot of people died from breathing this in from a leak, so we switched to methane, to natural gas. And we also added some stinky stuff into natural gas. But it's also called synthesis gas or syngas. And with this stuff here, well, you can make this from either coal or methane, and you react it with water, steam, to make synthesis gas. And you can, if you take synthesis gas and you react it over iron or chromium, you can get really high quality jet fuel or diesel fuel. And this is alternative fuels. And so Germany, Hitler, during World War II, he ran his war machine off of alternative fuels. So he did not have a lot of petroleum, And so he ran, and if you know some of the things like the Tiger tanks in World War II, they were diesel powered. They ran off of diesel. The American tanks, the Grants and the Stewarts, they ran off of gasoline. And it was much easier to destroy an American tank than it was a German tank. The armor was thicker in a German tank, and they used diesel instead of gasoline. Gasoline's high octane, it's really explosive. Diesel is not. So, and with World War II, one of the pushes was with the invading Russia. They were going for oil fields in Asia, and they were stopped at a town called Stalingrad. And actually, Hitler moved from the oil field objective towards the town of Stalingrad because of the name Stalingrad. So, because it had Stalin's name in it. And that's where the Germans stopped, and then the entire, I think it was the Third Army, if I remember correctly, the Third Army was surrendered then at Stalingrad. It lost a lot of soldiers that way. But with that though, the technology to make alternative fuels has been around for a long time. So a little bit more recent history, not super recent, but in the 1970s, country South Africa, they engaged in a series of laws and practices called the apartheid, and that was basically, it was dealt with racial discrimination. And the rest of the world didn't like that. They're saying, okay, we don't like that you're doing this, South Africa, so we're going to embargo you, and you're not going to get any oil. So what South Africa did was said, screw you, world. We know our history. We can make our own fuels. And so they did, using synthesis gas. So, and there's a company still in operation in South Africa called Sasol that is making alternative fuels using synthesis gas. And so what? Well, the Royal Air Force has come out and said, we use synthetic fuels in our jets. I'm pretty sure the United States does too, at least for our stealth fighters. Because petroleum-based jet fuel is dirtier. It gives soot, a lot of soot. Soot's really easy to track on radar. It's harder to track a jet that uses synthetic fuel. And the Royal Air Force has said, all right, we use synthetic fuels. So the United States is still tight-lipped about it, but we probably do too. I'd imagine that we do, at least for our stealth fighters. Also, so we don't really need petroleum. People talk about peak oil, like, oh no, what are we going to do when we're out of petroleum? Like, we'd be fine. We just have to switch our economy from petroleum to natural gas, probably, because there's a lot of natural gas reserves, especially in the bottom of the ocean. There's something called the methane hydrates. I mean, there's basically no way we could ever run out of those. There's so much natural gas in the bottom of the ocean. It's ridiculous.
What's enough digging into the ocean?
What's that?
Nothing.
Yeah.
Yeah, because that sounds like a great idea.
Well, yeah, I know, but it's
Have you seen the movie Meg? You really gotta
I haven't
increase
seen-
your movie watching that you do.
He
Because
watches a lot of TV.
this stuff has all been predicted in movies, and it never works out.
By The Simpsons.
The Simpsons. Well, I watched Thor Ragnarok this morning.
Hilarious! It's so funny. It's such a funny movie.
The Meg was so bad.
Okay.
No, the Meg was not good at all.
So why don't we run our economy off of natural gas and we still run off of petroleum?
Money.
Or yeah, we have a lot of infrastructure. We have trillions of dollars worth of infrastructure built up for petroleum. The other thing with petroleum, it's easier. So petroleum, it's a liquid, and you pump it. You pump the liquid from the ground. And natural gas, it's a gas. Petroleum's easier to handle than natural gas, because natural gas you have to pressurize, otherwise it'll escape. But it's not that much harder. But coal is the major pain. Coal is a solid. You cannot put it in a pipe. You have to put it on a rail car. And coal is also dirty. It's got lots of sulfur, so you have to wash the coal before you use it. And when you wash it, now you've got sulfurous water that you have to treat. So acidic water, and it's just a pain. So you have to mine it using machines. You can't like an oil well and a gas well. You can just stick a tube in the ground, and out stuff will come. So, but coal's hard to deal with. So, but petroleum is still the easiest, and it's also got the most energy per volume of anything, with the exception of uranium that you can find here on Earth. So that's why we're still using it. But, you know, we might go alternative fuels one day. We'll see. Okay, now, how much time we got? 10 minutes.
10 minutes.
So let's do a problem here, combining the other stuff that you've learned. Airbag volume is 11.8 liters. How much Na sodium azide is needed to fill an airbag at 1 atmosphere, 0 degrees Celsius? Has anyone ever been in a car accident and their airbag deployed? I have.
Many.
Yeah.
Yeah.
Oof.
Many.
You didn't
That's
I only have one.
in the car with.
Is your neck okay?
Yeah.
Man. All right. So I was in a car accident one time, and luckily I got long arms, and the airbag deployed, but it never hit me in the chest. I had a seatbelt on, so I never got to me. But I got a chemical burn on my arm. You can get that from the sodium. So sodium azide turns into sodium metal, which turns into sodium oxide, which can give you a chemical burn. So I had a chemical burn on my forearm from that. This is a problem for people though, because if you slam your head into the airbag, you can get chemical burns in your eyes. So the sodium metal can go in your eyes, and you can breathe it. You can breathe it, and then you can get a condition called pulmonary edema. Pulmonary edema is when your lungs fill with fluid, and then you start coughing and you can choke on your fluid. So that's what pulmonary edema is. So fluid buildup in the lungs. So airbags are actually pretty dangerous, and they use a chemical called sodium azide. And sodium azide, if you tap it, it explodes, and it turns into sodium metal and nitrogen gas. And that's what blows up an airbag real fast. So impact causes this, and it has a sound, and it fills up the airbag real fast with nitrogen gas. So I guess we're not going to have time to go through all this. I can.
Just kidding.
What? Okay. I guess I can work on it then. You can watch and learn. Okay. So you want to know how much sodium azide is needed to fill the airbag. So question is, what fills the airbag? That's the first thing that students have questions with. What's filling the airbag? What's filling the airbag is the nitrogen. So the nitrogen is the gas. It's the airbag. Air means gas. So nitrogen, that means the N2 is what causes the 11.8 liters. And what we need is mass sodium azide. And we can get the mass of sodium azide from the moles sodium azide. We can get the moles of sodium azide from the moles of nitrogen. And we can get the moles of nitrogen from the 11.8 liters. So, ideal gas law, PV equals nRT, and which implies N is equal to PV over RT. So pressure is 1 atmosphere, volume is 11.8 liters, R is 0.08206 liter atmosphere mole Kelvin, temperature is 273 Kelvin, and if I remember correctly, this is a half a mole. So 11.8 divided by 0.08206 divided by 273. This is 0.527 moles N2. So now we have 0.527 moles nitrogen. And then from the balanced equation, there is a 3 to 2 molar ratio. So 2 moles NaN3 over 3 moles nitrogen. And then, so nitrogen is 14 grams per mole, sodium is 23. So NaN3 is 23 plus 14 times 3 is 44 plus 23 is 65. 65 grams NaN3 per mole NaN3. Oh, come on, calculator. Okay. So the answer is times 2 divided by 3 times 65. You get 22.8 grams NaN3. Okay. I know I should have had you work on that, but I didn't think there'd be enough time. So again, why do people hate this class so much?
There's a lot of steps.
And they all come from previous stuff. You cannot forget anything at all. So yes, there are a lot of steps, but think of all the learning that's going on. Don't you leave, it's like a good workout, right? You leave this class feeling like your brain has been worked out, right? So, exactly. I'll get back on Monday. But you missed our speech. So, I'm giving people a week to make up, so some people don't make it. I'll give them a week, so on Wednesday, I would give it back to Keto. After Wednesday, then I take all the tests and I grade them. But then that means on Monday, I'll give everybody tests back. Then I will give you, then I'll also post the answer key with the solutions.
That's
So you
great.
can look at that, and then I give the retest to the 1st of November.
I gotta go home.
So you can learn from your mistakes and
Yeah, I passed.
yeah. But you did pretty well.
Yeah, I think I had the flu. I don't know for sure. I got hives. It's the only time I've ever gotten hives in my life is from the flu. But
Yeah. Oh yeah, I'm sorry.
No, I think that reading the book, because like I literally had no fucking clue what he was talking about until I went and I read the chapter. It's all right there. Yeah, it definitely does.
Okay, yeah. Okay, I'll put it in the testing center next week. So, but it'll be in there. I'll also write everything